Good afternoon, everyone. Thank you so much for joining us. I am Katie Rowley with the NOAA Central Library, and we are very excited today to bring you another NOAA Innovators Seminar. For a couple housekeeping things, if you are having any audio or visual issues, I recommend that you log off and log back in. That usually fixes most issues. If you are still having issues, please send me a chat in the chat box, or you can email library.brownbag@noaa.gov. We will be holding questions until the end of the seminar, but please feel free at any point to put your questions into the question panel. If we do not get to your question by the end of the seminar, please know that it will be passed on. And with that, I'm going to turn it over to Tiffany House to give our introduction today.
Thanks, Katie. I hope everyone is staying safe and healthy. I'm glad that you were able to join us today. My name is Tiffany House, and I am the NOAA SBIR Commercialization Specialist. The NOAA SBIR program provides competition-based awards to small companies for R&D and to transform their innovative ideas into commercial products. All SBIR proposals must directly benefit the NOAA mission and have excellent commercial potential. Carr Astronautics received an SBIR Phase 2 award in 2015, and his technology is still available as a sole source procurement for NOAA and other federal agencies under the SBIR rules. WxLiveStream is a subscription service providing subscribers without a GRB antenna with real-time access to GOES-R data products over the internet. WxLiveStream streams content as network common data form packets to facilitate immediate consumption by low latency user applications. This presentation will describe the genesis of WxLiveStream from an SBIR project, its service offerings, and cloud architecture. Before we begin the presentation, I'd like to tell you a little bit more about the presenter. Dr. James Carr is the founder of Carr Astronautics, a small business familiar in the NOAA community from his work on the GOES-R and GOES-NOP program. He has a Ph.D. in physics from the University of Maryland. His company specializes in atmospheric remote sensing and space technology. Now, without further ado, I give you Dr. James Carr.
Dr. Carr, we are not hearing your audio if you are speaking.
My apologies. Thank you. Yes, thank you for the very kind introduction, Tiffany, and Katie. Thank you for setting up the technical aspects of the webinar today. I'm very pleased to have the opportunity to address this audience. My company considers NOAA to be its anchor client, and we have been supporting NOAA's mission for more than a decade, going all the way back to the 2000 timeframe. So I'm going to talk about a product that has started as an SBIR, has its origins with an SBIR. But before I do that, let me just say a little bit about us. My company, Carr Astronautics, was established in 1991, so we've been around for a long time. We're still a small company, but we consider ourselves leaders in the field of environmental satellites, and we serve both NOAA and NASA. Our business spans actually 3 continents. We've done work here, of course, in the United States, and we've also done work in Europe and Asia supporting their environmental satellite programs, most notably Meteosat 2nd generation and Meteosat 3rd generation. And here in the United States, we are important contractors in the GOES-R community. We partnered with L3 Harris to develop the GOES-R core ground system, and we're actually responsible for authoring a significant fraction of the science software that runs in that GOES-R ground system. We have multiple other science activities and engineering activities with NOAA STAR and with Goddard Space Flight Center. And some of these are very exciting that I'd love to tell you about, but today I'm here to talk about real-time weather satellite data that we serve over the internet as a commercial activity. So I will very briefly provide, here's our outline here. So I'm going to very briefly provide an introduction to the GOES-R satellites. I'm assuming that almost everybody in the audience is familiar with them. However, there may be varying levels of familiarity, so I'll spend a very brief amount of time talking about the GOES-R satellites, and then I will describe our service offering, which is called WxLiveStream. WX is shorthand for weather, and we provide very low latency GOES-R data over the internet. This was an outgrowth of a Phase 3 SBIR activity that was sponsored by the National Weather Service. And we will give you a very short demonstration so you see some evidence that we're actually serving live data, and we'll show some integration with the Mercatus tool. Okay, so very briefly, GOES-R weather satellites. So the GOES-R carries two payloads that are weather related. One is called the Advanced Baseline Imager. We abbreviate that as ABI. And the other is called the Geostationary Lightning Mapper, and we abbreviate that GLM. There's an east satellite, which is GOES-16, and a west satellite, which is GOES-17. And I like to think of the ABI instrument as being a movie camera in space that is capable of performing three simultaneous tasks. One is a full disc movie, another is a continental US movie, and the third are mesoscale movies that can float around across the disk of the Earth. The ABI has the capability to image the Earth in 16 different spectral channels, and that includes red and blue, but no green, and that's going to be mentioned, come up later in my talk. And then it also has 4 reflective channel near infrared bands and 10 thermal channel bands that provide for full day-night imaging capability. So if you want to read about if you want to understand what these various spectral channels are good for, you can go to the GOES-R.gov website, which is a great resource, and you can find this ABI Quick Band information guide. And there's a fact sheet on each one of the 16 channels that describes its applications. And we serve data from all 16 of these channels in WxLiveStream. This is another convenient link, which is comes from CIRA, which is a cooperative institute at Colorado State, and it shows at reduced resolution animations of what the weather satellite is has recently seen. This is I'm showing this to you just to show you to illustrate the operations concept of the ABI. So these are the full disk images, and over several hour period from the east satellite. This is the view from the west satellite, and if we look at a CONUS, for example, this is the CONUS for 16. We can see the United States, the continental United States. There are also mesoscales. This is an example of a mesoscale, and the mesoscales are move around to various locations where the National Weather Service has priorities for imaging. So that's a very brief introduction to the ABI. The GOES Lightning Mapper is also on the two east and west satellites, and you can see in the right-hand panel here, this is a zoomed-in segment of showing some of an ABI image in true color that's showing some some thunderstorm convective activity, and the orange/red boxes that are overlaid on top of it are the counts of lightning flashes in those particular resolution elements. Okay. Okay, so what is WxLiveStream? So after that introduction to GOES-R, WxLiveStream is a subscription service, and it allows customers to access the data from the GOES-R series weather satellites live. Now, what I just showed you was not really live, because those images, those movie loops that we were looking at, had to be assembled after the full acquisition of a product scene. And I'm going to explain on the next slide what the benefits are of the WxLiveStream concept for users that have requirements to access the data from the weather satellite with low latency. Now, there is a way to receive the direct broadcast from each of the GOES weather satellites, and that is through through a broadcast from the GOES-R weather satellite to ground antennas, and it's called GOES Rebroadcast, GRB. And in fact, everybody that gets information, no matter how they get information, data from the GOES-R weather satellite, it at one time started as GRB, because that is the way that that GOES-R data is disseminated to all the user community, including NOAA. So you can buy a GOES-R rebroadcast GRB terminal and receive the live broadcast from the GOES-R satellites. However, if you need both GOES-16 and GOES-17, then you'll need to have two antennas, and antennas are costly. Antennas require maintenance. So the point of WxLiveStream is, by us receiving the GOES rebroadcast data, we are able to disseminate that over the internet to subscribers, and so that they can benefit from having access to the lowest latency data from GOES-R without owning the cost of ownership of an antenna. So our system streams what we call cloud and moisture imagery. That's reflectances and temperatures. And this is the what's called the KPP of the GOES-R system. It's the key product. and it's only tens of seconds behind when the actual weather happens on the Earth and is sensed by the instrument in space. I will explain how that works. We also provide a true color product. Remember, the ABI does not have a green channel, and there are several versions of this. NOAA has a version called GeoColor, and University of Wisconsin has a version of this called Natural Color. Ours is called TerraColor, and it is modeled after the same concept that NOAA distributes, but is not exactly the same product. We also provide a flash ascent density, which is a gridded product from the GOES lightning mapper, and this flash ascent density aggregates the lightning flashes that accumulate over a 5-minute interval, and it is gridded to 8 kilometers resolution. We have the ability to tailor subscriptions to user requirements, and I'll explain how that works too. So this is a very flexible, low-cost way to access data from the GOES-R system in real time. So this is how it works. So we have on the left something that we call a time-time diagram. Time-time diagram is a description of the activities that the ABI instrument is performing in space versus time. And so you read it like a book from left to right, top to bottom. So each line in the time-time diagram shows activities that are being conducted during those 30 seconds. The rows, bars, those represent the swath that the ABI is scanning across the face of the full disk. And to accumulate a full disk image, you start at the north and you step down to the south pole, and it takes approximately 10 minutes to acquire a full disk. Now, if you get the products from other sources, such as NOAA's PDA, you are downloading full disk products that are produced after the receipt after the scanning of the full disk itself. With WxLiveStream, you can actually use the data as it's being acquired in space by the ABI, and that those red lines are sort of trying to detect the scanning of the ABI, the full disk by the ABI, and you can receive our data just a few tens of seconds behind when it's actually being acquired in space, and you can use it right then and there. And so just to quantify what the latencies are, so on the right-hand side is have a depiction of the various steps that the data takes. So the ABI scans the Earth and it sends down the raw data, and takes about a second to do that, to get for the light to takes less than a second, actually about an eighth of a second for the light to travel down to the ground station at Wallops Island, Virginia. And inside the ground station, the data is converted into in real time. It's converted into a radiance product and packaged as GRB packets, and those packets are then uplinked to the GOES satellite. So in this process, we've got about 10-20 seconds of delay between when the ABI sees something on the Earth and when that data is uplinked to the GOES satellite, back up to the GOES satellite as GRB. Okay, so the GRB is then broadcast. That takes a very short amount of time, and it falls on the antenna that we lease, and we receive the GRB data there. That is then fed to us over the internet, to our Amazon Web Services cloud instances, where it is processed into the WxLiveStream packets and then delivered to subscribers. So that sort of gives you a characterization of what the latencies are between when the weather happens on the Earth and when we can, when a subscriber can receive the information about that weather. So here's a little depiction, an architectural depiction of how this works. So I show the, showing the antenna. We actually work with two antennas because we have service for GOES-16 and GOES-17. And those would stream into separate AWS cloud instances. So we have a cloud instance to process the raw data into the cloud and moisture imagery. And to do this, we have leveraged some COTS software that is provided by the Cooperative Institute in Madison, the Space Science and Engineering Center, their Cooperative Institute SIMS in Madison, Wisconsin. It's called CSPP. We have modified that for our processing, and then we distribute the data from the weather satellites from the ABI as packets, and each packet is consumable on its own as it is. You can see on the lower left there is a tiling diagram, and this shows the organization of the packets that are distributed. So we're showing the packets at 2-kilometer resolution. At the higher resolutions, 1 kilometer and half a kilometer, the packets would be decimated by 4 or 16, so that the volume in bytes for each packet is approximately the same for all packets in all resolutions. So a user can subscribe to any subset of these packets to tailor a subscription to the areas that they are interested in. We have had users who have only asked for packets since around Chile and Argentina and off in the Pacific Coast, and we've served them data in that mode. So each tile is actually a full product that can be consumed as is. And it can also be assembled at the user site, and that is done through what we call our consumer. Our consumer is a Java application. It's called a jar, and so you install the jar. When you become a WxLiveStream customer, you install a jar on your computer, and we provide you credentials to access the data stream. So it works out of the box, or you can tailor it to your needs and by various configuration settings, and assemble. You can work with the individual packets themselves that are streamed one by one, or you can assemble them into swaths of data to use once they're fully assembled as swaths, or you can, if you are tolerant to the latency allowed, the latency of waiting for a full disk, a full product to complete, you can assemble full products on your side as well, and forget about the tiles. This also integrates well with standard software like Macitus because it's NetCDF, and we'll see that in a minute. So here's an example of the consumer user interface. On the left-hand side, we have the real-time feed. All you need to do is start this up once. You we give you the host name, the VPN name, your subscriber queue name, and you get a username and a password, and that lets you access the live stream of data. There's various settings for building swaths, full products, etc. And we can also, the consumer also manages cleanup if that's something that you want to do. This is a truly enormous volume of data that's being served, so you need to be mindful of cleanup on your local machines or in your cloud instance. If there's an interruption in your internet service, we are continuously storing the data, the WxLiveStream data, in the Amazon S3 simplified storage system, and you can through the right-hand side, tab, the S3 tab on the user interface, you can access the data that you may have lost that has been stored on S3 and recover that way. So you don't need to go to class, for example, or PDA and pull the data that you might have missed. We offer subscriptions that can be tailored. There are, so here's a couple common options. Left-hand side shows the tiles associated with the full disk. You can also select the CONUS region, and South America is another popular subscription option. So, but really any subset of these tiles can be selected as a subscription option, and we can also decimate the data so that if you have no need for the red channel to be at a 0.5 kilometer resolution, but instead want it at 1 kilometer or 2 kilometers, we can decimate and serve you data that's decimated, and that lowers your bandwidth. Okay, so those are the subscription options. We also offer I mentioned TerraColor. So this is a true color product that can be served as well. And here's an example that I picked showing over CONUS, where you have a transition from day to night. So on the left-hand side, we have the daytime red, green, blue composite, where the green has been synthesized from something called normalized difference vegetation index. So there's a green flavor of normalized difference vegetation index and a red flavor normalized vegetation index. So we calculate one of those and then use a lookup table to construct the green channel to match. And the calibration between the red and the green flavors of normalized difference vegetation index has been made using MODIS. So this is a sound scientific approach to inventing the green channel from the, you can think of it as being invented from the near-infrared band 4, band 3, and we match it so that it produces the proper NDVI for that pixel. We also do resolution sharpening so that all the bands are sharpened to a 0.5 kilometer resolution, but that's not done at night, where we don't have access to any data from the highest resolution channel, which is the red channel. On the right-hand side of the picture, you can see the nighttime imagery, and it's a composite of bands 7 and 14 with some AWIP style enhancement color enhancement applied on top. we can look at the incredible detail in this imagery. So we're not going to claim credit for the wonderfulness of this imagery. This is NOAA's imagery, but this is just spectacularly beautiful. You can see, of course, the convective activity here in these clouds, and then if you can zoom in, and you can really see the incredible detail that this ABI sensor provides. Here's over California and the Rocky Mountains. This is actually the campfire from, I think that was November 2018. So we have this TerraColor product as well that we serve. Okay. So at this point, I want to ask that Solomon Jackson be the presenter momentarily, and he's going to show us a user interface, hopefully. So Solomon, why don't you very quickly say what we're looking at? This is a Macitas display. So we're serving data. This is recently served data that we've queued up into a loop in Macitas, and it's being updated with the very latest data from the weather satellite.
That's correct. The image will progressively build from the right to the left as it covers the United States. It loops constantly over and over, including fresh data that's recently been downloaded from the WxLiveStream cloud service.
So we're looking right now. We're looking at earlier in the morning, correct? Where the western United States is dark.
That is correct.
And this is band 3. So we support easy integration into Macitas, and we have had customers that have used our data with Macitas, there's a convenient way to run Macitas using Amazon Web Services desktops, which allows you to run your Macitas application in the cloud and exports the desktop to your view. Okay, so let's flip back to me as the presenter, please. Okay. Okay, so okay, last slide. So just want to conclude that we have developed a system to stream WxLiveStream's called to stream GOES-R weather satellite data as a customizable subscription service. We offer this. Really, this is sort of a niche market. The general public wouldn't really find much use for a lot of use for this particular product, because there are very few people that really need to know what the weather is right now versus what it was 15 or 20 minutes ago. This is we're really servicing a niche market. We price our product for enterprises. We have one big enterprise client right now, we don't widely advertise this and seek general public as subscribers, or have it's a subscription fee-based system. We don't generate any ad revenue. You pay a fee for a subscription. We like to do it a month at a time because it's some labor to set up subscriptions, and taking down subscriptions continuously is a burden for us. So we are really aiming this product at enterprises with with bona fide real-time needs that need to know the weather right now. This is a great solution if you don't want to have to deal with ownership of a GRB antenna or 2 GRB antennas, and provides just within 10 seconds the same latency that you would get from a GRB system that would do something similar to what we've got. I do want to put in a plug, however, that this is really something that NOAA could do, and we have written a white paper on this subject. I think NOAA, I would be perfectly happy if NOAA did this job instead of us, it's at least something, a distribution model that if it's not integrated within the NOAA enterprise for GOES-R, at least it's a distribution model that would be applicable for the next generation of environmental satellites, which I think we're calling GOES-XO. So thank you very much. If you have any interest in this product as a subscription, or you have an interest, or you know of some party that is interested in this kind of service, but doesn't know where to go, the email for subscription inquiries is listed here on the slide. Any inquiries regarding Carr Astronautics in general can be directed at me. And I'd like to thank you very much for your attention, and I'm pleased to have had the opportunity to present our SBIR-derived innovations in front of this audience. Thank you.
Thank you so much, Dr. Carr. Okay, we do have some questions, and as I'm sure you know, the first and most persistent one is, how much does your subscription cost? And there are variations on this question. Do you pay per tile? Do you have a range of costs that you can describe?
So we have listed prices in the past, and typically we just negotiate with individual users based on their specific needs. If you wanted to get everything from, everything possible at full resolution all the time, that would be approximately $2,000 a month, and we can negotiate and tailor subscriptions and we do negotiate and tailor subscriptions on a case-by-case basis. The cost of the main cost, there are two main costs for us. One is the antenna rental, and then the other is the other cost is the Amazon Web Services cloud, and it costs. These are fairly large instances that we run, and they run 24/7, and so when there's no issues with them, and occasionally there are, we're paying a significant amount of money to Amazon for the web services. So those are in the thousands of dollars per month. Then of course we have occasional labor costs to go in and fix problems and monitor to make sure it's running and so forth. We have from this experience learned that the paradigm of you have something, just put it in the cloud and it will work, has some nuances to it, and things do go wrong in the cloud. We do occasionally have dropped internet connections, occasionally have firewall issues, and very occasionally we'll have server issues.
Great, thank you. I'm not going to ask if NOAA gets a discount, so we'll move on to the next question. Tiffany would like to know how many people are signed up for this subscription service right now, and are you generating a fair or good amount of revenue?
So I would say that the commercial success of this is very mixed. So we have one enterprise client right now, and we have had episodic clients that will have a need. These are typically sort of science users that need to have access to real-time weather data to support aviation activities for data collects. And are sometimes going to places, remote places that are not terribly accessible. We have supported a couple of those campaigns, but the commercial success of this is decidedly mixed, and I think it's logically something that the government should be doing, and hence my comment on my last bullet on the summary slide here, something NOAA could do too.
Great, thank you. Okay, I'm going to move on to our next questions. Okay, this one's a bit of a two-parter. Mike is asking, is it requester pays for bandwidth when subscribing to feeds from a non-AWS environment on top of the standard subscription fees?
Okay, good question. The subscription, so what we do, I think the answer is the subscriber pays extra stuff. So what we do is we construct the cloud and moisture imagery as packets, and we use these packets are put onto into a system called, we use something called PubSub Plus, which is a Solus product, and it's an implementation of something called AMQP. So AMQP is sort of a way of delivering information from one source to another reliably, and so all of that's managed by the PubSub Plus software, and so we have that. You are, as a user, you are pulling data from that. You're receiving data from that virtual, what's called a virtual message router. So from the output of that virtual message router to the user, how that packet gets there is the user's undertaking. And if they need to pay extra for communications bandwidth to do so, that would be their burden.
Okay, thank you. The second half of that question from Micah is, which AWS regions do you host the services on for native AW access? Is it the same for both GOES 16 and 17?
Oh, great question. And we've actually had some bad experiences with this. So I believe we're running in the Ohio from out of a data center in Ohio. The proximity to our antenna is quite important, and we have played around with using different regions, and have had some problems with that, particularly when we were supporting a campaign in South America where we were looking for the best way to get data there. So I believe we run out of Ohio. I think Solomon maybe could answer that better than I could. So.
Solomon, do you want to chime in on that, or would you like me to move to the next one?
Yes, we do run out of a data center in Ohio. We have done demos in other regions. As Dr. Carr mentioned, latency is very important with this product. So because of where our data source is, we found that it's best to be as close to the data source as possible. That's it.
Great, thank you. I'm going to move to the next question. Ben asks, can you get data from the Russian LRPT satellite, which I believe is much higher resolution?
The short answer to that is no. So that would be interesting. What would be very interesting would be to integrate some of NOAA's other assets into this. So as some of you may know, there is a network of antennas that NOAA operates called, actually to be more precise about it, that University of Wisconsin Space Science and Engineering Center operates for NOAA. These are located across the United States, and then there's a larger network across the world. And these are steerable antennas that can be pointed at low Earth orbiting spacecraft as they transit overhead. And they can receive the direct broadcast from the low Earth orbiting satellites. And these would be, for example, the NOAA 20, which carries the higher resolution VIRS sensor, and other instruments as well, very important, CRIS, for example, and SNPP and MODIS, and also this network also supports the Sentinel, European Sentinel satellites. And I believe they can also acquire data from Chinese meteorological satellites. So what would be very interesting would be for NOAA to routinely access these overpasses of the polar satellites and use this system called Direct Broadcast Net, DBNet, to collect and centralize all that received data, and then it could be served in a similar fashion to how this geostationary weather satellite data is served. And so then you would have really very low latency access to these polar satellites as well.
Great, thank you. Next question is from Joanne. Is this live stream data being used in informal science education centers, museum settings? Could you kind of explain where it's being?
To my knowledge, no. So again, I said earlier, talking about our client base, we really see our market as being enterprises that are creating value-added. They're adding value to the data that NOAA is producing, and doing some application that really requires very, very low latency. And these kind of users are one example is disaster management, and another example is aviation. Those are the sorts of users that really that this low latency that we offer resonates with.
Great, thank you. Next question is from Edward. What types of applications generate demand for the Lightning Flash product?
Oh, great question. So Lightning Flash product So there is demand, and we are serving that demand. So the lightning, wildfires are a major source. I don't have the statistic at my fingertips, but a major source of ignition of wildfires is lightning. So having awareness of where lightning activity is occurring can be very beneficial in terms of alerting resources to the potential need to deal with a wildfire. Now, the real benefit to using the lightning mapper for that particular task is, and there's also terrestrial networks as well that are commercially available. But the real advantage to using the lightning data, be it terrestrial or from the GLM, the real advantage is that you know about the potential when the storm activity is occurring, and you have it you can localize it and determine where it's happening, where that storm activity is happening. You generally can't see the ground because there's a big thunderstorm going on, and the ground's obscured, so you can't apply the satellite wildfire detection algorithms that are prevalently used because the ground is obscured. So you get an early indication of the risk of wildfire activity by looking at the lightning data. So that's a very important use case.
Great, thank you. We are getting close to the 1 o'clock hour, so I'm going to ask as many questions as I can before we reach that. And so next up, could a National Weather Service program contract Carr Astronautics to use this capability to real-time stream custom products?
Absolutely, and I would love the asker of that question to send me an email. We'd be very happy to explore that with you.
Great, thank you. Another question from Micah. Have you considered using an AWS serverless workflow for the incoming data processing rather than the individual instances, Lambda, et cetera?
Oh boy, that's a question I don't have any idea how to answer because I don't even understand it. Let's see. I don't know if Solomon can answer that or not.
I can. We have looked at the different products offered by AWS, and eventually the plan is to transition to something of that sort. But for now, we're using the standard server infrastructure. One of the things we are excited about is the ability to scale the service based on customer needs and as well as reducing our resource usage. So eventually the plan is to move to such an infrastructure, but as of right now we're still just using standard servers. Thanks.
Great.
We also are exploring other cloud providers. Amazon is a great capability, but it's not the lowest cost provider.
Yes. Okay, so last few questions from Ben Jackson. Is a large, expensive antenna necessary? Could anyone pick up the transmission with a standard turnstile or V-dipole antenna?
These antennas this is a little bit more hefty equipment than your direct TV antenna. I don't have the cost information at my fingertips, but some of the high-end systems that the Weather Service owns lots of these antennas, and they should. That's a kind of key for them. Their systems, I believe, are in the hundreds of thousands of dollars, or at least $100,000 per unit. So it's a fairly large expense for capital expense for a small organization or a startup company. there's also a hidden cost with having an antenna. That's having to maintain it. If you are distributing the data over the internet from one or several antennas, several antennas is a good strategy, so you have site diversity to mitigate radio frequency interference, which is actually a problem in many places. So if you outsource that problem of maintaining the antennas and having site diversity to somebody else, then you have a better you're cutting your costs as well. So there's a benefit.
Great. I'm going to ask one more question. Larry Pollock is saying, your educational background is in physics. How did you get into the meteorology world? Oh, great question. So my training is actually in elementary particle physics, and I have a Ph.D. from the University of Maryland. I actually was working at Goddard Space Flight Center while I was a part-time graduate student, and I got involved in the GOES, one of the early GOES programs, and I really enjoyed it. So when I completed my degree, I had to decide whether or not I wanted to be an academic physicist or continue on working in the weather satellite world. I already had a developed career at that point in the weather satellite world, so I just decided to continue to do that. So just as an interesting note, I actually started my business in 1991, and my first customer was the European Space Agency for Mediasat second generation. So I went over and lived in Europe for 5 years, in France, to be exact, and worked in the early days as Mediasat second generation. So we are responsible for some of the engineering work that went into designing and building and testing that particular weather satellite system. That's amazing. Thank you so much, Dr. Carr. Finally, before we leave, will you be willing to share your presentation slides with those who tuned in?
Absolutely. I don't think I emailed you a copy, so I will do that after this meeting.
Perfect. Thank you so much. And that is the end of our questions. So I'm going to wrap it up for everyone, and we'll mail out Dr. Carr's slides when I receive them to everyone who attended today. Please remember that we did record this, and it will be posted shortly on the library's YouTube channel. And with that, I would like to thank Dr. Carr and Solomon Jackson and Tiffany House. And I hope everyone has a safe and good rest of their day. Thank you.
Thank you.